I'm going to talk about the insights on data challenge in deep learning projects. But so this lecture is the first one in a series. This specifically indulges in deep learning and lots of projects connected to it. But the next lecture is going to be for also machine learning people. It's going to be on research MLOps. Wait for the abstract, it's coming, and you'll understand how exciting it is. I wrote in the chat, and I'm saying here, if there are any questions left unanswered after the talk, hit me up on Reddit, Twitter, or LinkedIn. I have the same handle everywhere. So without further ado, let's begin. A little bit about Allegro. This slide is supposed to tell you that we're a serious company. We've been around since 2016. Mainly interesting are that we have two solutions. One is open source experiment management and MLOps. And the second one is more geared to enterprise. It also has to do with data. And this is why we're here today. We're talking about data management. And these are topics that we've chosen to talk about because they came up during the work with all the companies that we've dealt with, dealing with, and are going to deal with. And I try to make it very much entry level, but it's going to become complicated as we progress. So this is the agenda. We're going to talk a little bit about something called diminishing returns of data. Then we're going to briefly introduce the concept of active learning. If you haven't heard about it, it's a good place to start. And then we're going to touch the main event. We're going to do a almost deep dive into data imbalance and biases, and finish up with some summary and maybe, if we have time, Q&A. Great. So I don't know if you've heard, this is a very relevant subject. This weekend, there was an outcry in Twitter. Apparently, they have an algorithm, a deep learning algorithm, actually a pretty exciting one. I was very excited when I read the paper back in 2018. It basically, if you have a large picture and it has to be featured in your Twitter feed, it has to be cropped. So they do some smart cropping. But some users found that there's an edge case. So if you have a Caucasian on top and an African American on the bottom, only the Caucasian will be chosen. So this is obviously an edge case, but then people went around and found many other edge cases, which brought out this apology that we tested for bias, we didn't find any evidence, but it's clear that we have some more analysis. So, but the point is that, see, this is a fiasco, right? But the thing is that it's not the first time it has been talked about for the same algorithm. So back in 2019, Anima and Kumar, she said that if you have a woman and you're using the algorithm, it doesn't show your face. But also, let me just put a period here, because Twitter are not the only ones that have met with such fiascos on cropping, because Facebook, when they had this hidden figures IMDb poster, they cropped out the faces of the three African-American actresses only to show this very small faces of the Caucasian people. And they're saying, AI bias continues. And I like to see the sources of AI bias in this way. I call it the 5 Ds. It's the design or the algorithm itself. It's the developer. Mainly in deep learning, it's about the validation. And also it's data. This is 5 Ds. And Francois Cholet, who is you probably know him from Twitter, he's the creator of Keras. He's right, he's saying you can't just blame the data, because it's a very long process in which data is, the last link. But in order to meet that link, you have to be completely oblivious of the problem. So here we're going to discuss the problems. And this will give you an understanding which is not academic, it's a business savvy understanding. And I hope you will take it away from here and make use of it. So data management, when I'm saying data management, I'm talking about basically what's going to become the data set that you're going to train on. And we always start by saying, we're quoting Andrej Karpathy, from the head of AI in Tesla, that, when you're doing a PhD on deep learning, most of what you do is doing model and algorithms, and the data sets are already there. When you're doing real work in the real world, more than 75% of your time is going to be on data sets. And that's a very, very important point to note, because, you know, we used to say data science is 80% data cleaning, but it's more than that. It's just the entire thing is just dealing with the data. And the data can be very, very large. And this is where we're taking it into the first subject, which is called diminishing returns. So deep learning needs lots of data. That's kind of unequivocal right now. And to get the annotated data for your use case is going to be expensive because you need to hire people to label it. Specifically, if you're doing medical AI, the annotations has to be from doctors, and that's expensive and also complicated to do. And even more interesting is that, you know, if you have more and more data, your R&D is slowed down because you have more data to train on and more data to test on. So you have to take kind of grain of salt to the saying that give me as much data as I want. But do you actually need so much data? No. There's a law from economics called diminishing returns. What it means is that the more effort you do, you increase you know, number of annotated labels, images in this case, your accuracy gains for the same amount of data is going to be lower and lower. And I'm putting here a very small hint to the next topic. That's when you randomly sample from the population. That's what you probably always do. In deep learning, it really means that, you know, the more data you have, you would expect to see this effect. And we actually saw this effect with our clients. We can't talk about their data. We actually can't see their data, but we recreated everything in two very common data sets. It's called COCO, the Common Object and Context, and Berkeley Deep Drive. It's a data set for driving. So in COCO, you have various images with various subjects. In Berkeley Deep Drive, it's a data set for driving. So if you put a dash cam on your vehicle and you annotated everything, that's Berkeley Deep Drive. And this result is probably, if you're in a business, one of the most expensive graphs that you can make. Why? Because it says the number of annotated images and the metric, here it's map, the accuracy of your model. And we've done it for both data sets with two different models. A lightweight one, which will simulate maybe something that you will deploy, and a heavyweight one, which will be something you use for research and or for servers. And what apparent is the following. First of all, the larger accurate model reaches a higher accuracy asymptotically. Also reaches a higher accuracy almost at the beginning. But in order to know what is the asymptotic accuracy, you have to use many, many images, right? So imagine yourself, you're in a project and you have, you're just beginning and you have 10,000 images that you're starting with, and you know more will come. The consequences of this graph is the following. You will try and monitor this effect, and you will probably not succeed at the beginning because it's logarithmic, but it's very important to do so because you will be, when you feel like you're reaching this plateau, you can finally start to estimate how much more data is required to gain your metric of choice. You know, you're supposed to reach some kind of accuracy before you deliver. Also, it lets you decide how much data, how much resource to allocate more to the data and labeling. And most importantly, this is something people probably miss, is that once you get to this plateau, you can only here you can start changing models and seeing which one should you use. Okay, so this is a wisdom. It's empirical. recreate in various projects, take it away from here, do whatever you want from it. And there's a blog post that we wrote about it. It also applies in many machine learning tabular data. And it's one of my manager back in the days, he said that this one is one of the best managerial tools that he has for the project. So write it down and use it when you need it. Now, the next subject is very close. It's called active learning, and let's define what it is. As we said before, annotation is expensive and it takes a lot of time, especially if you do medical and so on. But you know, sometimes you have hours and hours and millions of images, and you will never be able to annotate all of them, especially when you know that you will have these diminishing returns. But not all data points were created equal. Okay, remember, there are some images that are more important than others. And I'm saying images all the time. We're giving examples from computer vision. I'm sorry, but for the few years, this is the leading subject in deep learning. Now GPT is starting to change that, but I'm sure that we can turn it so that you have examples from NLP and the sorts later on. But everybody understands vision, everybody understands the examples, so it's pretty good to do. But classically and without any loss of generality, as you say, in active learning, what you want to do is to somehow select the samples that you're training on so that you get the same accuracy for less data. Okay? You can have your academic definitions for it, but this is the simplest, most useful one. And how to do it? Well, if you don't do it, the process is very, very simple. You get raw data, you label it, you train, you get a model. If you're doing active learning, you get raw data, you select which images to label, you train, and you get a new model which helps you to select more images, and so on and so forth. And eventually you get a predictive model, presumably the same accuracy that you would get on a normal route, but with less images. So it means less money and less time. And I like this image because it's an oversimplification of what it does. It comes from linear classifiers in machine learning. Assume that the color dots are labeled class 1 and class 2 when you're trying to find the best classifier that delineates between the classes. If you just pick, let's say, image randomly, it might be this one. And this one is clearly a red image. But this image here might be blue, might be red. If this one is red, it's going to move the entire line. If it's blue, it's going to move the entire line. So we should label this one, right? And that's what people do. No, actually, if you read the paper, it's not exactly what they did, but if you squint hard enough and you apply it to a business case, that's exactly what we need, okay? The cyan curve is the random. There's a number of training images, and there's an accuracy measure for medical data. And in medical data, there are specific kind of images, healthy, sick, whatever, with all due respect. And they employed some kind of algorithm that has to do with active learning. And look, lo and behold, with less than 10,000 images, they get like 5 or 7 more points in the metric, which is a huge gain. And in order to get the same score, you need more than 10,000 images annotated if you annotate randomly. And the reason for that can be seen in this graph, and it's pretty simple when you think about it, right? If you choose randomly, this is the choices, the steps of taking the data and labeling it. If you choose randomly, you get a very small percentage of, let's say, sick people data, because there are more healthier people than sick, right? But if you do the active learning algorithm, it will select for you a nice mix of sick people. For example, you already get on this step that we discussed, we already get 20% sick, which is enough to get a good accuracy brewing up. So this slide comes to show you that this approach is real, it works. It's less fancy than the stuff that's going around right now with self-supervised, semi-supervised. Just put a pipeline, you do some student-teacher networks, and it works, okay? Takeaway message, you can get better results with less data. You have to use a special cycle for it, but you will get less training time for that, which saves you money, a lot of money, and you can get the product faster to the market, okay? And we also have a blog on this. I think it's the same blog, but you'll get the slides, you'll get the links, don't worry about it. Okay, now that we've spent about 20 minutes talking, it's time to touch the main course, which is data imbalance. You need to tune in and stop checking your Twitter feeds and whatever, and let's do this. This image is the average number of hits and location of hits on, I think it's a Flying Fortress bomber from the Second World War, which were collected from bombers returned from bombing runs. There are many legends about this, so I'm going to tell you my legend, which is shorter. You can look for the real story about it, but it's almost going to be the same. And back then, there weren't any data scientists, there were mathematicians, and the people from the defense ministry came and said, well, we have this data and we want to decide where to put protective plating on these bombers. However, we don't have enough weight capacity to put plating everywhere. So tell us, based on this data, where to put the plating. And I'm sure most of you already have the answer, but I'm going to expose it. If the planes manage to return home, that means that all the red points are hits that were not actually important to protect from because they made it back home. So only the places where there aren't any hits are places where the planes never came back home and should be protected. So this is a very simple and clear example of survivorship bias or data imbalance. It means that the data that you're seeing is just a subset of the population, and sometimes it's the completely unimportant subset of the population, okay? And sometimes that's what you have in data sets. And there are two sources that there are other sources, but these are two main sources for data imbalance. The first one is the natural class imbalance. If you're looking at Berkeley deep drives and you're looking at dash cam footage, so naturally you will see more cars than dogs, right? But also when you're sampling the, let's say, data set which should represent the entire world, if you are not collecting it correctly, it will inherently have some kind of imbalance. For example, if you're doing, again, driving, you will have more daytime data than nighttime data, okay? And this can be shown from these graphs. I'm sure that the numbers are slightly too small for you, but it's class prevalence for Berkeley deep drive. You see most of it's car and some traffic signs. And in Coco, most of it's person and some other classes. And so from this data imbalance, there are also two kinds of data imbalance, right? So first one is very clear to understand, it's prevalence. As I said, some classes appear more than others, but there are also frame imbalances. In the same data point, or in the case of vision frame, there are certain classes that appear more than others. So there are distributions within distributions inside your data. And I'm going to explain it deeply, maybe in 2 slides from now. So have some patience. But the point is that all of them are important. So let's start with object imbalance. Let's look at Berkeley Deep Drive. There are lots and lots of objects. There are actually 700,000 cars, 30,000 trucks, but only 3,000 motorbikes. Now think to yourself, if you're training a model based on this data and you want it to recognize motorcycles, motorbikes, how confident are you as a researcher or developer to send off this model, even though it says to you, yeah, I have 80% accuracy on motorcycles. Yeah, it has 80% accuracy on whatever motorcycles that it has. You obviously need more motorcycles, right? So this is one kind of imbalance. Another kind of imbalance is the frame imbalance that we discussed. And what does it mean? If we look at each frame, okay, and we count the number of frames where car appears in, lane appears in, or person appears in. So 70,000 frames have cars versus only 20,000 frames have trucks and only 2,000 frames have motorcycles. Let's look at also at person, because person is important if you're training an autonomous car. If you don't have enough people, you won't be able to identify people correctly, and then accidents happen. And there are other ways of looking at this. I'm not expecting you to really grok or understand everything right now, but you will revisit these slides afterwards. I'm sure it will trickle down. But also, there are, again, if there are classes that appear together, instances of the same class appear together. If you're in a road, there will be many, many, many cars. So 10 cars per frame. Or if there are people, there are 4 people per frame. But if you're a bike, you will have only 2 bikes per frame at most. What does it mean? That means that if you're trying to compensate for all these imbalances, some things are impossible to compensate. And the way to see it is a step level in complication. It's kind of it's called data entanglement correlation matrix. So it means that the correlation of if I have a car in my image, what's the chance to have a person in my image? Or if I have a person in my image, what's the chance to see a car in the image? So you see, it's not symmetric. And all of this area is black. And that's good for us. If it's black, it means that we can somehow resample the data and gain some of the balance back into our data. But all of this means that we are kind of captivated by the real world biases. We need to do something else. Okay, so what do you do? There are 2 options. Let's talk about the model level, because it's the easiest one to explain. We can change the model, specifically people change the loss function to account for the imbalances. In terms of if you want a before model, it can reproduce the loss surfaces, okay, that you can get if you had a perfect data sampling, supposedly. And it can also overcome entanglement, because if you're saying for a certain image, in this image, don't pay attention to the cars so much, pay attention to the people. So that image automatically becomes skewed towards the people, and it helps you to fight that imbalance, okay? But the thing is that if you only have a few images, for example, a car, or as I said, a motorbike, then once you get that image, the classifier for that image is going to get a very large signal. So it's going to get a huge correction, which can drive everything off and hurt convergence, and it will take you longer to converge to the values that you would expect, okay? I know this is complicated, but and for some of you like me, it's very late, but we have to discuss this, okay? So again, theoretically it's sound. It helps you with the entanglement, but it's really hard to converge on it. Conversely, okay, if you attack the situation in terms of data, okay, well, you can't, as I said, resample to get the perfect distribution of data, but you are able to sample the rare classes with higher distribution. You're going to change everything. That was the black part where in the last slide. And that means that you have many gradient updates, which helps convergence because you're always fine-tuning your weights in everywhere, okay? And does it work? Well, everything works. If you take the baseline, okay, and we're talking about the average precision in IOU of 50% per class, it means that you were able to classify correctly and also locate in the image with a pretty good accuracy. It's not perfect. For practical purposes, you would want to have an IOU of 0.7, but 0.5 means it works. So the baseline is pretty bad for the motorbike, the motorcycle, the bike, the bus and truck are okay, the car are okay, but person is completely hideous, right? So you wouldn't trust the model to detect the people if you're letting the car use that model. So then you can use something called focal loss. You heard about it. That's the kind of model weight change the loss thing. And it helps, okay? It helps a lot in some cases. Sometimes it doesn't. That's exactly the point that I was making with the rare classes. Then if you do a data set resampling or selection, it helps amazingly. And actually, I don't want to talk about this a little bit, but I just mentioned it in a few words. If you use something called naive inverse marginal ratios to resample the population in terms of loss, you get, it's a little bit more complex than focal loss. It helps almost as data, but not in the places where you would expect it, okay? So this can be an entire talk of 2 hours. The point is that there are methods to do it. And it seems like the naive one of, just resample the data correctly so you can have an equal probability to get motorcycle or person or car inside a single batch, then you get the most oomph, okay? By the way, this data set is not so good because you see, even though you do it, you still can get more than 0.2 for a person. That can also tell you that there are problems with the annotation or the actual distribution in the acquisition process. But that's not for today, okay? Time for the real big takeaway messages that I think you should all pay attention to, okay? As we said in the beginning, data is very important for the convergence of the model, okay? And the imbalance of the data is key to the problems that you're going to encounter in the development process. You're going to spend 75% of your time doing this. Now, if you're aware of this, if you're aware of all the problems and you're not getting an entire data set in the beginning because that's not how businesses are working, you can try to change that. You can send people to the field to take more pictures of persons. You can have balanced batch distribution results. If you use this kind of data-based resampling, okay, it will have help you a lot in the cases where we discussed that we have this entanglement, but mostly in the areas where you have rare classes. And this is something that we're really proud of. That's something which we're talking about a lot with our customers. You have the distribution of the data. The data set can be dynamic, and you can treat the ratios and the sampling distributions of the objects in your data as a hyperparameter. You can tune it, you can fine tune it, you can get bigger results, okay, with the same data, just by doing hyperparameter tuning on the distributions. It's a very expensive tip learned here. Okay, yeah, let me just take a look if there were both Q&As and chats, right? Let's see if before I summarize, if there are. How do I do it?
Yes, I think the main. I see quite a few questions in the Q&A.
So okay, so let me summarize and we'll answer everything. But there were also some stuff in the chat, right? Anything important?
Yes, I think yeah. I mean, we can look at both.
Yeah. Okay. Let's see them now because they might be more important. Yeah. All of the slides will be shared. Yeah. And great. Let's continue and summarize. If we already took a break, I can also take some water. That's good. Again, with Andrei Kapati, okay? I think that you would agree with me. I've shown you that data management is important, but also all these tricks that we did with the data sampling, they gave us a big return on investment. And that's exactly what the head of AI in Tesla is saying, right? We see more significant improvement from treating the data training distributions than doing all of the model architecture searching. So if you should just take off-the-shelf model, deal with your data problems, make sure that you have a good data set. Then you can start trimming, changing, I don't know, distilling, whatever you want. That's a guaranteed route to project success. And why am I saying it? It's because there was a survey about what's wrong with your work. And it's a good survey, I recommend reading it. And the top 2 reasons of problems in the projects was training data, not enough. And it was very, very, very problematic. So we discussed it. It's not always a problem of the quantity, it's also what you're labeling, so use active learning. And also, pre-processing is horribly annoying, okay? And it takes, it's prevalent. And so this data resampling is a major pre-processing time hog. And it's actually one of the reasons that we exist as a company. So this is like a partial shopping list. I don't know if you're working or you're training and you're gonna work in the future. This is what you want in order to make sure that you can treat your data problems and not have a fiasco. It's data versioning. It means that you can do version control or revisions on your data. If you're changing something, you can roll back, okay? And that you can, even though most of the data is going to be on the cloud, that you don't need to know where it is. You don't have a physical hard drive where the data is that you have to access. And it helps you from losing data. Data caching means that when you're training, your machines will have already the data set on them, so you don't have to download it. And that costs a lot of time accumulatively. You need some way to do what we used to call exploratory data analysis, but now we just say data visualization. You need some data annotation and tagging. There's actually quite a few free solutions that I can recommend if you hit me up on Twitter. And then if you want to do real work, you will probably mix in external data sets with your data. And then you would need to do conforming of the labels on the fly. And that's something that you want to reconsider when you're designing your infrastructure. And most importantly, if you want to do these tricks with mixing data sets or resampling or whatever, you need to be able to use the data set as a database. You need to be able to query it. It's not enough just to do random shuffle, give me images, let's do 7 epochs and see what happens. It's definitely not enough. And I think I've proven to you that that is the case. And it's not just me speaking, it's the experience of several very important companies. Okay, now, before I answer questions, there are a few, let's break for commercials, right? So Allegro Trains is 2 parts. One is open source, and I urge you to check it out. I'm not going to speak about it today because today is data, but we also have data solution. And we think that it's important to have your experimentation platform and data solution and MLOps in the same platform, because we need some kind of lean stack. You don't need to be depending on many, many bits and pieces that can fall apart. You need to put your eggs in a few baskets. Okay, so Allegro Trains should be one of them if you're doing data. Yeah, I'm not a salesman. I'm not a salesman, right? So I can't really sell you this, but what we offer is amazing. All of this is for free. You can download it and start working today. It's resource optimization, full visibility and control of everything. Also research MLOps and MLOps. We can work on everything from your office servers to DGXs and manage resources. The integration is completely ridiculously simple. And if you're an enterprise, you're willing to pay, we have like stuff that are light years away from what you would expect. So talk to us. Great. So we work with everything. Everything is magically integrated. Check it out. Okay, it's awesome. Let's do Q&A. Thank you very much for listening.
Great, thanks Ariel for a lot of informations. And let's move to the Q&A. If you can click the Q&A tab, I see we have quite a few. We can start from Q&A first and then check the chat.
Okay, we have 6 in the Q&A. Let's see if I can answer. Whatever I don't answer today, I promise to either answer in our next entailment of the series or online. So, resource code library packages to do active learning. Okay, so as I said, Allegro Trains, open source. I'm going to actually, before the end of 2020, going to release an example of how to do active learning for free with pipelines and everything. But data management will be on you unless you use some kind of product. Okay. It's basically the diagram I've shown you here. Where is it? Yeah, this one, right? So you just draw it with a graph, and that's what happens. Okay. Obviously, if you want it already made, there are products. There are also competitions to us, but I recommend us, of course. That's a great question. Okay. Definition: bad classes are rare. Okay. As I said, you just resample. Okay. It really helps. You know, we just say for each car, give me a person. It works. Okay. Rule of thumb to detect imbalances. Yes. You just count. Okay. It's exploratory data analysis. I'm also same person, right? Good questions. New metrics. There are many ways to do it. Basically, you just ingest the data once into a pandas data frame and just draw it, right? It's very, if you can't do it, then you need to first learn how to do it, because that's the bread and butter of our profession. How can we calculate co-occurrence bias from any data set? Well, any data set that will have instances where you have appearances, okay? So if it's audio, it's images, maybe some tables, right? In tables, it's much easier. It's just everything is there, okay? And then it's just a matter of calculating Pearson correlation metrics or whatever. I mean, the code is really, really naive. But basically, I can't discuss a lot of it because some of this is proprietary, but there are solutions that are open source, and if you hit me up later on Twitter, I'm willing to discuss everything about it. Let's see, how do we do with data imbalance? What's detecting, adjusting in regards to text data? Well, I wish I could really help you because I'm not a very good expert on NLP, but it's almost the same. Okay, if you're doing sentiment analysis, okay, and you have sentences that appear like the unhappy guest, unhappy or resent or whatever appears in fewer times, then you just upsample that. Okay, you just have to do some pre-processing, get your annotations, view the data once, resample it, and go again. Risk of sounding silly, I like these. Verify that the errors of active learning teachers are tolerable. I don't think you sound silly. It's difficult for me to understand the question. I can verify that the errors active learning teachers machine learning algorithms are tolerable. Yeah, actually, it's a basic QA algorithm. You get results, you plug them into a stronger model that is, for example, if you're trying to do something for the edge, so you have a model that is really, really lightweight, and you have a very heavy model. So you do, it's called student teacher. It can verify that what you've done with the smaller model helps. Okay. Let's say you're going to annotate 1 million pictures and 1 million images. Then you can't annotate all of them with the stronger model. You want to annotate them with the weaker model. So you just select a few and you do some kind of QA process and see how many of them passed. Okay, I hope that helps. How do you make sure model predictions make sense with train in just a few observations? The same way you make sure that they make sense if you have a lot of observations. You choose a metric and you adhere to it. Also, sanity test with your eyes. That's why debug images are very, very important. It's why you use TensorBoard or Allegro trains. These correlation metrics and code increments are the same. Well, it's a correlation metrics I mean, they're not the same, but they're almost calculated almost the same, and you can just Google it. It's not that complicated. Gilad, Nivo pays people to do the initial labeling. Oh yeah, so there are many companies that are employed in a lot of places in the world to annotate data. Okay, the point is that some data you can't share. Some data is confidential. Some data is you need experts to annotate. And in those cases, active learning is important. Also, once you start getting images from if you're deploying and you have images from the real world, okay, your data intake is going to explode. You're going to have bazillions and gazillions of images. Which ones of those are important? Which one of those will increase the accuracy and improve your product? That's active learning again. So you can't just pour all your money into annotations. Can Allegro trains be only used for that and not training? Well, you can use Allegro trains for everything. You just you do the integrations, but you have to write the code. Neometrics, just hit me up on Reddit, Twitter, LinkedIn, whatever you want. I'm glad to help. Okay. Any more questions?
I see there are still quite a few. I'm not sure. Are we on for the Q&A? Can you go to the top? Are we already covered all of them? I just double check.
Let's go to the chat. Interesting. Shared. No, yeah, we've done everything. Great. So I hope to see all of you next time. And again, it's going to be a lot about MLOps and automations and pipelines, and how to build stuff like this on your own with almost no external libraries that you need to learn, just Python and Allegro trains. Great. So without further ado, I thank you all for being here, and thank you, Bill, for AI Camp.
Okay, great. Thanks. Yeah, I'm saying this is a great talk. You know, have a lot of insight on the labeling service and also the training product. Some of the practical experience. I see one more question is coming up in the chat. Maybe you want to take a quick look.
So thanks.
In the chat.
Yeah, something from Rex, I think.
Yeah, some from Rex.
Rex, okay. Said that there was some algorithm that started with the Q to check for active learning errors. Yeah, QA. No quality analysis, quality assurance. You have pass-fail. It's pretty basic. You can do better than that, and we actually do better than that, but you have to pay for it. Basically, whatever works for you. Okay? Great. Okay.
Okay.